Welcome viewers. In this video we'll see the solved problem based on the transformer EMF equation. Subscribe this channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we'll go to the first problem. Problem 1. The maximum flux density in the core of a 250 voltage bar 3000 voltage 50 Hz single phase transformer is 1.2 Weber per meter square. If the EMF per turn is 8 voltage, calculate the primary and secondary turns and area of the core. So, in this is coming under the single phase transformer, the frequency 50 Hz, the voltage is 250, primary voltage 250 and secondary voltage 3000. Flux density is 1.2 Weber per meter square. EMF per turn also given 8 voltage. We need to find primary and secondary turns and area of the core. So, based on the given data, the maximum flux density BM is 1.2 Weber per meter square. The V1 is given 250 voltage, primary voltage. Secondary voltage V2 is 3000 voltage. The frequency is 50 Hz. EMF per turn is given as 8, that is nothing but E1 by N1 and that is equal to E2 by N2. So, we have the relation E1 by N1 equal to 8 or E2 by N2 equal to 8. We need to find the value of N1 and N2 as well as the area. So, from this EMF per turn is given that E1 by N1 equal to 8. So, that from that we can write N1 equal to E1 by 8. Interchange these two. E1 by 8 equal to N1. So, that E1 is already given 250 voltage. So, 250 divided by 8, 31.25 turns. So, the primary turns is 31.25. So, by round off you can take it as 31 or 32 turns. Similarly, this EMF per turns can also written as E2 by N2, referring the secondary side equal to 8. So, that N2 equal to E2 by 8. By interchanging these two, E2 by 8 equal to N2. E2 is already given 3000 voltage, secondary voltage is 3000. So, 3000 by 8 is nothing but 375 turns. So, the number of turns available in the secondary is 375. Now, we will go to the area. We need to find the area of the core. So, it is given as the flux, the maximum flux equal to flux density into area. That is, the flux density equal to flux by area. From that, flux equal to flux maximum flux density into area. So, our aim is to find the area. So, A equal to pi m by Bm, maximum flux divided by maximum flux density. This maximum flux density is already given in the formula. Bm is already available, but we need to find the pi m value. The flux is not given. So, from pi m and Bm we can calculate the area. So, now we will see how to find the pi m, maximum flux. So, we know that the EMF induced in the primary is given as the one more formula available, E1 equal to 4.44 F pi m into N1. EMF induced in the primary. This F is the frequency, pi m is the maximum flux, N1 is the number of turns available in the primary winding. So, in this all the values are available, E1 is available, pi available, N available. So, from that we can find the pi m value by rearranging this pi m, that is this all these parameters are brought in the denominator. So, pi m equal to E1 divided by 4.44 F into N1. Right, these terms are brought in the denominator. So, the E1 is 250 voltage and 4 divided by 4.44, F is 50 and N1 is given as 31.25. That is we calculated the primary number of turns, primary turns N1 we calculated 31.25. So, by simplifying this what we got 0.036 Weber. So, the maximum flux pi m equal to 0.036 Weber. Now, we got this pi m value as well as Bm value already given, pi m value also calculated, so that we can easily calculate the area of the core. So, area of the core A equal to pi m by Bm. Pi m is 0.036, just now we calculated, divided by Bm is given 1.2. So, by simplifying this what we got 0.03 meter square. So, area of the core is 0.03 meter square. So now we calculated number of turns in primary N1, number of turns in N2 as well as area of the core. Now we'll go to the second problem. A single phase transformer has 500 turns in primary, 1200 turns in secondary. The cross sectional area is 80 square centimeter. If the primary winding is connected to 50 Hz supply at 500 voltage, calculate the peak flux density and voltage induced in the secondary. So the peak flux density means maximum flux density. So from this formula the given data are N1 is given, number of turns is 500, number of turns in primary winding. Similarly number of turns in secondary winding, N2 also given 1200. The area also given, A equal to 80 centimeter square. In our while converting into meter, it is 80 into 10 to the power minus 4 meter square. Right? Centimeter mean we need to multiply with 10 to the power minus 2. Here centimeter square is there. So it is multiplied by 10 to the power minus 4. And primary voltage is given, applied voltage. Voltage applied to the primary winding is 500. We need to find the flux density, maximum peak flux density and voltage induced in the secondary. So we know that the EMF induced in the primary, E1 equal to 4.44 F pi m into N1. This is a very basic formula, EMF induced in the transformer. So in this E1 value is given, applied voltage is given, frequency is given, N1 also given. So that from that easily we can find the pi m, peak flux density or maximum flux density. So bring all these term in the denominator, so that pi m equal to E1 divided by 4.44 F into N1. So the E1 is given as 500 divided by 4.44 into the frequency is 50 Hz. Number of turns in primary is 500. So by simplifying all this value, we got the pi m equal to 4.504 into 10 to the power minus 3 Weber. So the maximum flux we calculated, but what we need is flux density, right? 4.504 into 10 to the power minus 3 Weber. But what we need is maximum peak flux density, Bm. Bm is nothing but pi m by A, maximum flux divided by area, right? So that we'll get the flux density, area already given. So the pi m we calculated 4.504 into 10 to the power minus 3 divided by area, area is 80 into 10 to the power minus 4 meter square. So by simplifying this, what we got, 0.563 Weber per meter square. So the peak flux density or maximum flux density is 0.563 Weber per meter square. Now we need to find the voltage induced in the secondary winding, voltage available in the secondary winding. So that can be calculated from the transformer turns ratio, V2 by V1 equal to N2 by N1, right? Based on the transformation ratio formula, we have V2 by V1 equal to N2 by N1. In this, what we need is V2. So that this V1 is multiplied here. So V2 equal to V1 into N2 by N1. The V1 value already given, number of turns N2 and N1 also already given in the problem. So that V2 equal to this number of voltage applied in the primary is 500, number of turns in secondary is N2 is 1200, number of turns in primary N1 is 500. So by simplifying this, we got 1200 voltage, that is this 500 and 500 got cancelled. So we are getting 1200 voltage. So voltage induced, EMF induced in the secondary winding is 1200 voltage. So we calculated the peak flux density or maximum flux density and voltage induced in the secondary winding. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening. Welcome viewers, in this video we will see the solved problem based on the transformer on loaded, when the transformer is loaded condition. This is a part 1. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Now we'll see the problem 1. A 3300 voltage bar 300 voltage a single phase transformer gives 0.6 ampere and 60 watts as a ammeter and wattmeter reading when the supply is given to the low voltage winding LV winding and high voltage winding is kept open. Calculate the magnetizing current and iron loss component. So this is coming under the open circuit test. The high voltage side is kept open, the supply is given to the primary winding. Right. Now we'll see what are the given data available. So the current flowing in the primary I naught, because there is no load is available, so it is called as a I naught, 0.6 ampere. W naught, power taken by the primary winding under the no load condition, so that it is W naught equal to 60 watts. And primary voltage is 300 and secondary voltage is 3300 voltage. Here the low voltage side, the voltage is applied to low voltage side and high voltage side is kept to open, so that 300 is taken as V1, 3300 is taken as V2. See this the ratio available here. This 300 side is taken as a primary winding, 3300 is taken as secondary winding, that is kept open. Now we need to find the magnetizing current and iron loss component. So the power is given by this wattmeter reading is given is available. So that is nothing but V1 I naught into cos pi naught. The power given by the wattmeter reading, the power taken by the transformer under no load condition is nothing but V1 I naught into cos pi. So from that we can find the cos pi value. So that cos pi equal to, bring this V1 and I naught in the denominator. So that cos pi naught equal to W naught divided by V1 I naught. W naught is given 60 watts and V1 is 300 and I naught is 0.6. So all these values are available, I naught, W naught and V1. So by simplifying this, what we got, 0.33 power, the cos pi naught equal to 0.33 is a lagging. The value is 0.33. Now we got the value of the cos pi. From that we can easily find the magnetizing current and the iron loss component. So the magnetizing current I mu is given as I naught sin pi naught. The already formula is given. It's a magnetizing current. That separate video available for the no load condition. So cos pi naught equal to 0.33 we calculated. So that pi naught equal to cos inverse 0.33, that is equal to 70.52 degree. The angle between current and voltage pi naught is 70.52 degree. So I mu equal to I naught sin pi, that is equal to I naught value is 0.6 into sin pi. Pi value just now we calculated. So sin 70.52. So by simplifying we got 0.566 ampere. So the magnetizing current is 0.566 ampere. This magnetizing current is the responsible for producing the flux in the primary winding under no load condition. And then we will see the iron loss component. This iron loss component responsible for the iron loss happen in the primary winding. IW equal to I naught cos pi naught. So that is equal to I naught is 0.6 into cos pi naught already available. Cos pi naught is, that is cos pi naught equal to 70. This pi naught is 70.52. So cos 70.52 is there. So by simplifying this, what we got, 0.198 ampere. So the iron loss component is 0.198 ampere. So we calculated both the magnetizing current and iron loss component. Now we'll go to the second problem. A 3300 voltage bar 220 voltage 30 kVA single phase transformer takes a no load current of 1.5 ampere when the low voltage winding is kept open and the iron loss component equal to the 0.4 ampere. Calculate no load input power, magnetizing component and power factor of the load current. We need to find the no load input power, then magnetizing component and power load, power factor and the no load condition. So this low voltage winding is kept open. So based on the given data, the V1 or E1, the voltage applied or voltage induced is 3300 voltage. V2 or E2 is 220 voltage. This data is available. And kVA is given as 30 kVA. This kilovolt means it multiplied by 10 to the power 3. So 30 into 10 to the power 3 VA. Then no load current I naught is given 1.5 ampere. The IW, the working component, is given as 0.4 ampere. Right. So this current is the 1.5 ampere. This iron loss current is 0.4 ampere. So these are all the given data. So from the no load input power is given. No load input power. This we first will find the no load input power. That is nothing but W naught equal to V1 I naught into cos pi naught. First question is no load input power. W naught is V1 I1 cos pi naught. Right. But the IW is given. IW equal to I naught cos pi naught. Right. This IW is given, that is equal to I naught cos pi naught. So that W naught is written as V1 into this I naught cos pi naught is nothing but IW, because IW value is given. This cos pi value is not available. So we can replace I naught cos pi naught as a IW working component. So V1 is available 3300. The iron loss component is given 0.4. So by multiplying this we got 1320 watts. Right. So this is the formula. In this value is replaced by IW, because IW value, the working component current is given, pi naught is not given, so that we are replacing. Now we got the no load input power 1320 watts. Now we'll go to the magnetizing component. So the magnetizing component and power factor. So IW equal to I naught cos pi naught. So cos pi naught can be calculated as IW divided by I naught. These two values are available. So from that we can find the cos pi naught. So that is 0.4. Working component is 0.4. The no load input current is 1.5. So by simplifying, what we got, 0.267. The cos pi naught, the angle between current and voltage. This cos pi naught, this is pi naught. The angle between current and voltage is pi naught. The cos pi naught value, what we got, 0.267. Now we'll concentrate to find the magnetizing component, I mu. So I naught square equal to IW square plus I mu square. Based on the vector diagram, we can write like this. This is the I naught, the no load input current is the vector sum of IW and I mu, working component and magnetizing component. So bring this IW in the left hand side. So I naught square minus IW square equal to I mu square. So you can rewrite that I mu square equal to I naught square minus IW square. By taking square root on both the side, so I mu equal to square root of I naught square minus IW square. Now substitute this value. I naught is available 1.5 ampere, IW is 0.4 ampere. These two values are given. So by simplifying this, we got 1.44 ampere. The magnetizing component is 1.44 ampere. So we calculated the power factor cos pi, magnetizing component 1.44 ampere, as well as the input, as well as the no load input power. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the transformer on load, the part 2. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we'll go to the problem. A single phase transformer with a turns ratio of 440 bar 110 voltage takes a no load current of 5 ampere at 0.2 power factor lagging. If the secondary supplies a current of 120 ampere at a power factor of 0.8 lagging, calculate the current taken by the primary winding. So the voltage is given, the no load current and no load power factor is given, and the loaded current and that power factor also given. We need to find the current taken by the primary. So by analyzing the given data, the V1 equal to 440 voltage. the primary voltage is 440 voltage and V2 is 110 voltage. Then I naught is 5 ampere, no load current. For that the power factor cos pi naught equal to 0.2. Under the loaded condition, the current taken by the secondary is I2 equal to 120 ampere. For that corresponding power factor cos pi equal to 0.8. So the voltage is available, no load and full load current also available. We need to find the current taken by the primary winding. So from this cos pi naught equal to 0.2, so that pi naught equal to cos inverse of 0.2. So that value is 78.46 degree. Similarly, cos pi 2 is given, that is equal to 0.8. From that pi 2 equal to cos inverse 0.8. So the cos inverse 0.8 is 36.86 degree. So now we got the value of pi naught and pi 2. Now we will see that the I1 square, the primary current. The question is we need to find the primary current. That is nothing but vector sum of I naught and I2 dash. Vector sum of I naught and I2 dash is nothing but primary current taken by the primary. This I2 dash can be calculated as K into I2. This I2 is given in the problem, right? So the I2 dash equal to K into I2. Then I will find the K value transformation ratio is V2 by V1. K equal to V2 by V1. V2 is 110, V1 is 440. So that 110 by 440 equal to 0.25. So the transformation ratio is 0.25. Now we got the transformation ratio, so that we can calculate I2 dash. I2 dash equal to K into I2. So the K value is 0.25 is calculated into I2 value is 120. So by simplifying that we got 30 ampere. The I2 dash, the current due to loading of secondary is called as I2 dash, that is 30 ampere. So based on this value we can draw the vector diagram. So this V1 is taken as a reference. The voltage in the primary winding is reference. The pi is out of 90 degree out of phase with V1 because I mu, the magnetizing current, is responsible for producing this pi. That magnetizing current is lagging the voltage by 90 degree. So that in this x axis we are taking the value pi. So the no load current I naught is 5 ampere. No load current is I is 5 ampere. For that the corresponding angle is 78.48. That is we calculated. From cos pi naught we calculated the pi naught value. So this angle is 78.6 degree. Then I2 dash, this I2 dash is 30 ampere. We calculated I2 dash is 30 ampere. So that is the angle is pi 2. Pi 2 equal to 36.86. So that also we calculated from the cos pi 2. Right. So I2, so I naught is no load primary current is 5 ampere, that is at an angle of 78.6 degree, that is calculated from this pi naught, and I2 dash is 30 ampere at an angle of 36.86 degree, that is calculated from the cos pi 2. Now this I1 is nothing but vector sum of I naught and I2 dash, vector sum of these two. So this angle, the difference in angle between this I naught and I2 dash is calculated as 41.6 degree. So that also available here. The angle between I naught and I2 dash is the difference between these two angles, 78.6 minus 38.86, that is equal to 46.6 degree. So that can be taken as theta. The angle between I naught and I2 dash calculated as 41.6 degree. From the diagram also we can calculate. So from this angle and the I naught value and I2 value, all the values are available. So easily we can calculate the I1 value. The I1 is nothing but vector sum of I naught and I2 dash. What is I naught? I naught is the current flowing through the primary under loaded condition, no load condition. I2 dash is the under loaded condition. So vector sum of these two is nothing but the total current I1. Then how will you find the I1 value? Using the parallelogram theorem of vectors. I1 dash I1 equal to square root of I naught square plus I2 dash square plus 2 into I naught I2 dash into cos theta. So this is the formula available for using the parallelogram of vectors. This I naught value is available, I2 dash value also we calculated, and this theta, cos theta, theta value also calculated. The angle between this I naught and I2 dash. Now substitute all the values. I naught is 5 ampere, so 5 square. I2 dash we calculated 30 ampere, so 30 square plus 2 into I naught is 5, I2 dash is 30 into cos theta. The theta value is 41.6 degree. So by simplifying this for all this value and taking the square root, we got 33.9 ampere. The current taken by the primary, the total current taken by the primary is 33.9 amperes, right? So from this vector diagram we can easily calculate. So this I1 value is 39.3 amperes. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the solved problem based on the transformer and load, the part 3. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the problem. A 400 bar 200 voltage single phase transformer is supplying a load of 50 ampere at a power factor of 0.866 lagging. The no load current is 2 ampere at 0.208 power factor lagging. Calculate the primary current and primary power factor. So this is the current taken at the full loaded condition. This is the current taken at the no load condition. Now we'll analyze the given data. The V1 is given, primary voltage. Primary voltage is V1 is 400 voltage. The secondary voltage is given, V2, 200 voltage. Then I2 is the full load current, is 50 ampere. The corresponding power factor cos pi 2 equal to 0.866. So this current and power factor is the loaded condition, 50 ampere and 0.866 power factor. Then no load current is 2 ampere, is given as 2 ampere. For corresponding power factor cos pi naught is 0.208 value, the corresponding power factor. We need to find the primary current I1 as well as primary power factor cos pi 1. We need to find I1 value and cos pi 1 value. Now we have the cos pi 2 as well as cos pi naught. These two values are available, cos pi 2 and cos pi naught. From that we can find the pi 2 value and pi naught value. Cos pi 2 equal to 0.866, so that pi 2 equal to cos inverse 0.866. So this value is 30 degree. So the pi 2 value is 30 degree. Similarly cos pi naught equal to 0.208. So that pi naught equal to cos inverse 0.208. So that is equal to 77.99 degree. Right. So from that we can find sin pi naught. So sin pi naught value is 77.99, that is equal to 0.978. So now we calculated pi 2 value, that is 30 degree, pi naught value 77.99 degree, and also sin pi naught value 0.978. So by using this we can draw the vector diagram. So we need to find the I1 value. I1 is nothing but vector sum of I naught and I2 dash, right? I naught and I2 dash. Now we'll see this is the I naught value, no load current, that is given as 2 ampere. It is drawn at an angle of this 72, at an angle of this 77.99 degree by using this degree pi naught, and I2 dash is given as 25 ampere. So this angle is 30 degree by using this 30 degree pi naught, pi 2 value, right? So this I naught is 2 ampere drawn at an angle of 77.99 degree using pi naught value. This I2 dash is 25 ampere, it is drawn at an angle of 30 degree. So this I1 is nothing but vector sum of I0 and I2 dash. I0 and I2 dash, right. So this angle between this I2 dash and I0 is the difference between these two angles. By using that we can find. By using the parallelogram of vector, we can find the I1 value. Now we'll see that I0 is 2 ampere, so that I2 dash, we need to find I2 dash is K into I2, right. So that K equal to V2 by V1, that is 200 by 400, 0.5. Transformation ratio is 0.5. This 25 ampere we can calculate like this. Only I2 is given, I2 dash is not given. I2 is given as 50 ampere. I2 dash is 25 ampere. I2 means current flowing through the secondary. I2 dash mean due to that current flowing in the primary is called I2 dash. I2 means current flowing in secondary. I2 dash mean current flowing in primary due to the loading of secondary, right. So I2 dash equal to K into I2. I2 already available 50 ampere. K is 0.5 calculated here, so that is 25 ampere, right. So this 25 ampere is calculated from this formula. Now we can calculate the I1 value. So the angle between this I0 and I1, I2 dash, is the difference between these two angles, 77.99 minus 30 degree, that is equal to 47.99 degree. So that is given here. The difference between these two angles is 47.99 degree. So now the angle is available, I0 value available, I2 dash value available. So by using parallelogram theorem, we can find the I1 value, right. So using the parallelogram theorem, I1 equal to square root of I0 square plus I2 dash square plus 2 into I0 I2 dash into cos theta. So by using this parallelogram theorem, we can find the I1 value. All the values are available. Theta also available. Theta is nothing but 47.99. So this I0 is 2 ampere, I2 dash is 25 ampere. This we calculated into plus 2 into I0 2 ampere, I2 dash 25 ampere into cos 47.99 degree. The theta is 47.99 degree. So by simplifying this, we got I1 equal to 26.38 ampere. The current flowing in the primary winding is 26.38 ampere. So that is given here. So this I1 is vector sum of these two. The angle also we calculated by using parallelogram theorem. We calculated this I1 value 26.38 ampere. Now we will calculate the power factor, primary winding power factor. So we know that I1 cos pi 1 equal to I2 dash cos pi 2 plus I0 cos pi 0. From the vector diagram, we can easily identify that this I1 is the vector sum of I2 dash and I0. So that I1 cos pi 1, this cos pi 1 is nothing but primary power factor. I2 dash into cos pi 2, cos pi 2 is nothing but secondary power factor when it is loaded, in plus I0 cos pi 0, cos pi 0 is nothing but power factor under no load condition. So this is the power factor under no load condition, this is power factor under loaded condition, this is power factor in the primary winding. This I1 cos pi 1 equal to 22.066, right. So from that cos pi 1 equal to 22.066 divided by I1. So that cos pi 1 equal to 22.6066 divided by I1 value we calculated 26.38. So by simplifying what we got 0.836. So the primary power factor is 0.836. So in this video we calculated the primary power factor as well as the primary current. Subscribe the channel for more videos and notification. The soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the transformer test. This is OCAC test, part 1. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we'll go to the problem. First we'll see the problem 1. In the no load test of a single phase transformer, the following data were obtained. The primary voltage is 220 voltage, secondary voltage is 110 voltage. Primary current is 0.5 ampere, primary power input is 30 watts. This is for no load test. These data belongs to the no load test. Find the turns ratio. First one is turns ratio, second one magnetizing component of no load current, third one working component, fourth one iron loss. The resistance of the primary winding is 0.6 ohm. So first we will analyze the given data. So the V1 is given 220 voltage, primary voltage is 220 voltage, secondary voltage is 110 voltage. No load current, under no load condition, current taken by the primary is 0.5 ampere. Power input to the primary winding under no load condition is 30 watts. So from this data we can easily calculate the turns ratio, N1 divided by N2 or V1 divided by V2. That is 220 divided by 110 voltage, V1 divided by V2, that is 2. The turns ratio is 2. Then the power input is given, no load power input is given in the problem. So the W naught is nothing but V1 I naught cos pi naught. So from that cos pi naught can be written as W naught divided by V1 I naught. Right? By rearranging this equation we can write. This W naught value is given as 30, V1 is 220 voltage, I naught is 0.5 ampere. So by simplifying this we got 0.2727, cos pi naught equal to 0.2727. So that pi naught equal to cos inverse 0.2727, that is nothing but 74.17 degree. So the pi naught, that is the angle at the no load, current and voltage, the angle between current and voltage under the no load condition. That angle is 74.17 degree. Now we need to find the magnetizing component and working component. We note that IW equal to I naught cos pi naught. This I naught value is available 0.5 ampere, cos into pi naught. Pi naught is we calculated now. That is, this cos pi naught is directly we can substitute 0.2727. That is equal to 0.1363 ampere. So the working component is I naught cos pi naught, that value is 0.1363 ampere. Then the magnetizing component is I naught sin pi naught. This cos pi naught here sin pi naught. So I naught is 0.5 into sin of pi naught. Pi naught value is 74.17. So sin 74.17. So by simplifying this we got 0.4810 amperes. The magnetizing current is calculated. Now we need to calculate the iron loss. The final question is iron loss. So the input is nothing but iron loss plus copper loss. The input what is given, that is converted into iron loss and copper loss. So from that, iron loss equal to input minus copper loss. Right? Because we need a iron loss value. So from input we subtract the copper loss, we can get the iron loss. What is the input given? 30 watts. Already given us no load input is 30 watts. How will you find the copper loss? I naught square into R. I naught square already given 0.5 ampere and R value is also given. Resistance of the primary winding. So by simplifying this we got 29.85 watts. The iron loss is 25.85 watts. So now we calculated turns ratio, magnetizing component, working component and iron loss. Now we will go to the second problem. The primary and secondary windings of a 30 kVA 6000 bar 230 volt single phase transformer have resistance of 10 ohm and 0.016 ohm respectively. The reactance of transformer referred to the primary is 34 ohm. Calculate the primary voltage required to circulate the full load current when the secondary is short circuited. What is the power factor of short circuit? So this problem coming under short circuit test. Right? The voltage is given kVA rating is given, resistance and reactance are given. Now we'll analyze the what are the data given in the problem. The kVA is 30 kVA. The kVA given as 30 kVA. Primary voltage is 6000 voltage. Secondary voltage is 230 voltage. Then R1 and R2, the resistance of primary and secondary winding. R1 is 10 ohm, R2 is 0.016 ohm. And the reactance is given. Reactance referred to the primary winding. So that's the total reactance. X01 is 34 ohm. Secondary reactance also transferred to primary. So the reactance referred to primary means the total reactance 34 ohm. So from this we can easily find the turns ratio. K equal to V2 divided by V1. V2 is 230, V1 is 6000. So by simplifying we got 0.0383. The transformation ratio is referred to this transformer is 0.0383. Now we can find the equivalent resistance referred to the primary. So our final aim is to find the power factor of the short circuit. So R01 equal to R1 plus R2 dash. R2 dash mean the secondary resistor is transferred to the primary. R2. R2 is the secondary resistance. While transferring into the primary, it become R2 dash. So R1 plus R2 is the total resistance in the primary, referring the primary winding. Is transferred to primary winding. So the R1 plus R2 dash can be written as R2 divided by K square. So R1 is 10 ohm, R2 is 0.016 divided by K value. The transformation ratio we calculated 0.0383. So by simplifying we got 20.907 ohm. So this is the total resistance of the transformer referring to primary. All the values are transferred to the primary. So that value is 20.907 ohm. Now we will find the impedance. Impedance referred to the primary. Z01 equal to square root of R01 square plus X01 square. The general formula. Impedance equal to the sum of the resistance and reactance. So the R01 we calculated 20.907. X01 is given in the problem itself 34. So by simplifying this we got 39.99, that is nearly 40 ohm. Reactance of the transformer referring to the primary is 39.99 or it is equal to nearly equal to 40 ohm. Now we can calculate the current from the kVA rating and voltage. So I1 equal to kVA divided by V1. Right. So the kVA is nothing but V into I. So that by dividing V1 we will get the I1 value. So kVA is given as 30 kVA, 30 into 10 to the power 3 divided by primary voltage is 6000. So by simplifying we got 5 ampere. Current flowing in the primary winding is 5 ampere. From that we can find the VSC, short circuit voltage in the secondary side. It is ISC into Z01. So this I1 is nothing but the short circuit current. Both are same. The I1 is equal to ISC also. So 5 into 40, that is this 40 is available. So it is 200 voltage. Short circuit voltage is 200 voltage. Now we can find the power factor. Power factor, one general formula available, R01 divided by Z01. R01 we calculated 20.9 divided by Z01 39.99. So by simplifying we got 0.522. This power factor is 0.522 value. Right. So in this problem we calculated the turns ratio, then equivalent resistance referred to the primary, then equivalent impedance refers to the primary, then current, short circuit voltage. Finally we calculated the power factor under the short circuit condition. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening. Welcome viewers, in this video we will see the solved problem based on the transformer test, OCSC test, so part 2. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. First we'll see the problem 1. Obtain the equivalent circuit of a 200 bar 400 voltage 50 Hz single phase transformer from the following test data. OC test, open circuit test, 200 voltage 0.7 ampere 70 watts on the LV side, low voltage side. Short circuit test, AC test, 15 voltage 10 ampere 85 watts on the high voltage side, HV side. So the data is available as OC test and AC test data are available. So then other data are V1, V1 equal to 200 voltage, primary voltage. I0 is 0.7 ampere. First we will see the OC test, right? The voltage applied to the winding is 200 voltage because the OC test is performed on the low voltage side. And no load current is 0.7 ampere, no load power input to the transformer is 70 watts. So from that we can find the transformation ratio V2 by V1, 400 by 200 equal to 2. The transformation ratio is 2. First we are considering the OC test. So from the no load power W0 is V1 I0 into cos pi naught. From that we can find cos pi naught equal to W0 divided by V1 I0. By rearranging this equation we can find. The W0 is 70 watts and V1 is 200, I0 is 0.7. All these values are available. V1, I0, W0. So that is equal to 0.5. Cos pi naught equal to 0.5. If cos pi naught equal to 0.5 means pi naught equal to cos inverse 0.5, that is 60 degree. So the no load power factor is 0.5. The corresponding angle pi naught, the angle between no load current and voltage is 60 degree. Now we can calculate the magnetizing component and working component. The magnetizing component IW equal to I0 cos pi naught. So the I0 is 0.7, cos pi naught is 0.5. So that is equal to 0.35 ampere. So the IW is calculated. Then the magnetizing component I mu equal to I0 into sin pi naught. That is 0.7 into sin 60. The pi naught value is 60 degree. So by simplifying we got 0.606 ampere. So now we calculated IW value and I mu value, working component and magnetizing component. And other two parameters what we need is R0 and X0. During the load and no load condition we need 4 parameters. One is IW, I mu, R0 and X0. The current IW is flowing through the resistance. The current magnetizing current is flowing through the inductance. So we need to find R0 and X0 value. R0 equal to V1 divided by IW, working component. Already we discussed that the iron loss happen in the this resistive. The magnetizing current mean it is inductive. So 200 divided by 0.35 is 571.42 ohm. Similarly the reactance V1 is X0 is V1 by I mu. So that is equal to 200 divided by 0.606, it is 330 ohm. Now we calculated all 4 parameters IW, I mu, R0 and X0. So that we can draw the equivalent circuit for the open circuit test. Now we will go to the short circuit test, AC test. So the secondary short circuit voltage is given 15 voltage. The secondary current I1 equal to IS equal to 10 ampere. This is the short circuit current. When the short circuited, the current flowing. Then short circuit power equal to 85 watts. Now we will find the Z02. Z02 equal to VSC by ISC by referring the secondary circuit. So 15 by 10, these two values are available. VSC and ISC available. So it is 1.5 ohm. Then Z01 referring the primary side is Z02 divided by K square. So that is 1.5 divided by 2 square, it is 0.375. So we got the Z02, Z01 value. Then WSC equal to ISC into RS, R02. So the power input, power during the short circuit. WSC equal to ISC square into R02. So that from that we can find the R02 value. R02 equal to WSC divided by ISC square, that is 85 divided by 10 square, that is 0.85 ohm. So, these data are available. Now, we calculated the R02 value and Z01 already calculated. Now, refer the equivalent circuit. This is for the no load condition, that is a open circuit condition. This R0 and X0. This R0 and X0 we already calculated. Similarly, IW and I mu also we already calculated. Right? This R01 we need to calculate R01. We see later. This X01 also we need to calculate R01 and X01. This Z01 is available, R02 is available. From that we can calculate R01 and X01. Now, we will see how to calculate R01 and X01. So, this is the equivalent circuit. This refers the no load component, this refers the short circuit components. So, R01 equal to R02 divided by K square. R02 already calculated 0.85 divided by 2 square, that is 0.2125. So, the R01 is calculated. X01 equal to square root of Z01 minus R01 square, Z01 square minus R01 square. Z01 is calculated 0.375 minus R01 also we calculated 0.2125. So, that is equal to 0.308 ohm, right. So, in the equivalent circuit this R01 and Z01 also calculated. So, by using this all the value we can draw the equivalent circuit. Now, we will go to the second problem. A 2000 bar 200 voltage transformer has primary resistance and reactance of 2 ohm and 4 ohm respectively. The corresponding secondary values are 0.025 and 0.04 ohm respectively. Determine the equivalent resistance and reactance of primary refer to the secondary. Total resistance and reactance refer to the secondary. Equivalent resistance and reactance of secondary refer to primary. Total resistance and reactance refer to the primary. So, we need to find the both referring primary as well as secondary values. So, the data is given are the V1 is given 2000 voltage, B2 is 200 voltage, primary voltage is 2000, secondary voltage is 200 voltage. Then R1 is given 2 ohm, primary side resistance, primary side reactance X1 is 4 ohm. Similarly, secondary side resistance 0.025 ohm, secondary side reactance 0.04 ohm. So, we know that we can transfer all the data from primary to secondary as well as secondary to primary. For example, this R2 and X2 can be transferred to the primary side. Similarly, this primary data can be transferred to the secondary side, so that the calculation become easier, right. So, that is called a equivalent resistance. The separate video available, link is given in the description box. So, accordingly it is saying referring to primary, referring to secondary. So, before going to that we will find the transformation ratio V2 by V1. So, 200 divided by 2000 it is 0.1, is the transformation ratio is 0.1. Now, we will go to the first one. The first one is the equivalent resistance and reactance refer to the primary winding, refer to the secondary, R1 dash and X1 dash. R1 is the resistance of the primary, R1 dash mean while it is transferred to the secondary side, refer to the secondary side. Similarly, X1 is the reactance of primary, X1 dash mean it is transferred to the secondary side. So, that equivalent value is R1 dash equal to K square into R1. So, while transferring to the secondary side it will give the same effect. So, that in order to make the same effect it is multiplied by K square. Similarly, X1 square equal to K square into X1. So, the K value already calculated 0.1 square into R1, R1 value is given 2 ohm, that is equal to 0.02 ohm. Similarly, K square into X1 value is 4, 0.04 ohm. So, this R1 and X1 is nothing but the equivalent resistance and reactance of primary while transferring to the secondary side. R1 means primary value, R1 dash mean it is transferred to the secondary. While transferring we are multiplying with the K square. Then we will go to the second division, R02 and X02. So this is nothing but equivalent resistance and reactance referring to the secondary side. It means the primary resistors are transferred to the secondary side. Primary resistance and reactance is transferred to the secondary side, so that R02 equal to R2 plus R1 dash. R2 is the resistance of secondary. R1 is the resistance of primary. R1 dash mean it is transferred to the secondary side. Right. So by adding this we will get the total resistance referring to secondary side. Similarly, reactance also. Right. So R2 value is 0.025 plus R1 dash, that is we calculated. R1 dash is 0.02, that is 0.045 ohm. Similarly, X02 equal to X2 plus X1 dash. So X2 is already available, 0.04 plus X1 dash is we calculated, that also 0.04. So that is 0.08 ohm. Right. So these two are nothing but equivalent resistance of a transformer referring to the secondary side. R0 to X0 means secondary side. Same thing will go for a primary side also. We will find R2 dash. That is, the third question is equivalent resistance and reactance of secondary refer to the primary. So this R2 is the resistance of secondary, while transferred to primary it become R2 dash. Similarly, X2 become X2 dash. How will you find R2 dash? Is R2 divided by K square. So in the previous case it is multiplied by K square. So while transferring from secondary to primary, normally it is divided by K square. So 0.025 divided by 0.1 square, it is 2.5 ohm. Similarly, X2 dash equal to X2 divided by K square, 0.04 divided by 0.1 square, it is 4 ohm. Right. So these two are the equivalent resistance and reactance of the secondary while transferring to the primary side. Now we will find the fourth one, total and resistance and reactance referring to the primary. This one secondary. These two are secondary. Total resistance referring to the secondary. This one referring the primary. Right. So R01 equal to R1 plus R2 dash. R2 dash mean secondary resistance transferred to the primary. R1 is 2 ohm. R2 dash just now we calculated 2.5 ohm. So it is 4.5 ohm. Similarly, X01 equal to X1 plus X2 dash. X1 is given 4 ohm. X2 dash we calculated, that also 4 ohm. So totally it is 8 ohm. So this is the equivalent resistance and reactance of the primary referring the primary winding. So in this we discuss about the SC test as well as the resistance and reactance transfer from primary to secondary as well as secondary to primary. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the solved problem based on the regulation of transformer part 1. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. We'll go to the problem. 100 kVA transformer has 400 turns on the primary and 80 turns on the secondary. The primary and secondary resistance are 0.3 ohm and 0.0 ohm respectively, and the corresponding reactance are 1.1 ohm and 0.035 ohm respectively. The supply voltage is 2200 voltage. Calculate the equivalent impedance referred to the primary, voltage regulation and secondary terminal voltage for full load having a power factor of 0.8 leading. Now we will see the given data. What are the data available? The N1 is given as 400, number of turns in the primary is 400, number of turns in secondary N2 is 80, R1 primary resistance 0.3 ohm, secondary resistance 0.01 ohm, and the rating is given 100 kVA. V1 is 2200 voltage, supply voltage applied to the primary, and power factor is 0.8 leading. Reactance of the primary is 1.1 ohm, reactance of the secondary is 0.035 ohm. So then we need to find the equivalent impedance, voltage regulation, secondary terminal voltage for a power factor of 0.8 leading. First we will find the transformation ratio, K equal to N2 by N1. So that 80 by 400 it is 0.2. The transformation ratio of the transformer is 0.2. Now we will find the R01, that is the total resistance of the transformer referring the primary side. R1 plus R2 dash. R2 dash mean the secondary resistance is transferred to the primary, so that it is given as R2 dash. So R1 plus R2 dash will give the total resistance of the transformer. This R2 dash is nothing but R2 divided by K square. In order to make a equivalent, it is R2 dash is nothing but R2 by K square. So this R1 is already available, 0.3 plus R2 is 0.01 divided by K. K is 0.2. So 0.2 square, that is equal to 0.55 ohm. So the total resistance of the transformer referring the primary side, that is secondary resistance is transferred to the primary side. So that we got the equivalent resistance is 0.55 ohm. Similarly, the reactance X01 equal to X1 plus X2 dash. X2 means the reactance in the secondary, while transferred to the primary it become X2 dash. X2 dash is nothing but X2 divided by K square. In order to maintain the same effect, X2 dash is nothing but X2 divided by K square. X1 is available 1.1 plus X2 is 0.03 divided by K square is 0.2 square. So by simplifying we got 1.975 ohm. The total reactance of the transformer primary and secondary is nothing but 1.975 ohm. Now we will see the equivalent impedance. First question is we need to find the equivalent impedance referred to the primary side. So Z01, we know that the sum of resistance and reactance is nothing but the impedance. So Z01 equal to R01 square plus X01 square, square root of R01 square plus X01 square. R01 and X01 is calculated. This is R01 value and X01 value. So the square root of 0.55 the square plus 1.95 the square, that is equal to 2.05. So the equivalent impedance referred to the primary is 2.05. The first question is equivalent impedance. Now we will find the voltage regulation. Voltage regulation. For that, first we will find the no load voltage. V20 is nothing but a no load voltage, that is nothing but E2, secondary voltage. So that can be written as K into E1 by referring the transformation ratio K into E1. This E1 also replaced by V1. V1 is voltage available, voltage applied, E1 is the voltage induced, both are equal. So K value is available 0.2 into V1 is given 2200, so it is 440 voltage. So the no load secondary voltage is 440 voltage. By using the formula we calculated. Similarly R02, R01 and X01 is already calculated. Now I will calculate R02 and X02. R02 equal to K square into R01, because in the regulation we need these parameters. So K is 0.2 square into R01 is 0.55, that we calculated. So R02 is 0.022 ohm. Similarly X02 equal to K square into X01. So 0.2 square into 1.975. So the equivalent value is 0.075 ohm. So now we calculated secondary terminal no load voltage R02 and X02. Resistance and reactance of the secondary side we calculated. Then we will find the I2 value. Secondary current, secondary side current is kVA divided by no load secondary voltage. From this formula we can find the current flowing in the secondary winding. The kVA rating is given 100 kVA. So the kilovolts, so that it is multiplied by 10 to the power 3. The no load secondary voltage we calculated 440. So that is equal to 227.27 ampere. So the secondary the current flowing through the secondary is 227.27 ampere. Now we can calculate the voltage regulation. The formula for voltage regulation is I2 R02 cos pi minus I2 X02 sin pi divided by no load secondary voltage. So we know all this value. I2 is calculated now. R0 to X0 also available. No load voltage also available. This cos pi is given 0.8. Power factor is given as 0.8. From that we can find sin pi is 0.6. Now we can substitute all the values. I2 equal to 227.27 into this I2 is commonly available between these two parameters. So this is taken outside. R02 is 0.022 into cos pi is 0.8 minus X02 is 0.079 into this sin pi is 0.6 into 100 divided by 440. So by simplifying this, what we got, it is minus 1.39, 1.539. The voltage regulation is minus 1.539. Right. Now we'll go to the secondary terminal voltage. The formula for secondary terminal voltage is V2 equal to E2 minus I2 Z02. So general formula is E2 equal to V2 plus I2 Z02. The voltage induced in the secondary is equal to the voltage available at the load terminal plus losses. So that we can write V2 equal to E2 minus I2 Z02. Right. So the E2 minus this I2 Z02 can be written as is a impedance. We can express in terms of resistance and reactance. I2 R02 cos pi minus I2 X02 sin pi. These values are available. So E2 is 440 minus 227.27 into 0.022 into 0.8 and 227.27 into 0.079 X02 and sin pi is 0.6. So by simplifying we got 446.7 voltage. So the secondary terminal voltage is 446.7 voltage. So in this problem we calculated the first we calculated the transformation ratio, then equivalent impedance referred to the primary side, voltage regulation and secondary terminal voltage. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the solved problem based on the regulation of the transformer part 2. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we'll go to the problem. First we will see the first problem, problem 1. Calculate the value of voltage regulation at 0.8 power factor lagging for a transformer with resistance drop is 2% and reactant drop is 4% of the voltage. So the power factor is given and resistance drop and reactant drop is given. So from this we can analyze the given data. The power factor cos pi equal to 0.8. If cos pi is 0.8 mean automatically we can write sin pi equal to 0.6. And the resistance drop is given, that is denoted by VR. So VR is nothing but I2 R02 divided by no load secondary voltage V20. Right. So this is given as 2%. So the resistive drop is VR, that is nothing but I2 R02 divided by secondary terminal voltage, that is equal to no load secondary voltage, that is equal to 2. Similarly, the reactance drop Vx is nothing but I2 X02 divided by secondary no load voltage, that is given as 4%. So these are all the data given. From that we need to find the voltage regulation. So the voltage regulation is the formula is I2 R02 cos pi plus or minus I2 X02 sin pi divided by no load secondary voltage. Now we'll split the terms. I2 R02 divided by no load secondary voltage into cos pi plus or minus I2 X02 divided by no load secondary voltage into sin pi. So this I2 R02 divided by no load secondary voltage is VR, because VR value is given. So into cos pi plus or minus I2 X02 divided by no load secondary voltage, that is nothing but Vx, the reactance drop, into sin pi, because these two values are given. So that we can take this is the VR and this term as Vx, and plus or minus is given. This plus for lagging power factor, minus for leading power factor. So in this problem it is given as lagging. So we can take plus symbol. So 2 into the resistance drop is 2 into 0.8, cos pi is 0.8 plus for lagging. Vx is reactance drop is 4 and the sin pi value is 0.6. So by simplifying this we got it is 4%. The voltage regulation for the given problem is 4%. Now we'll go to the second problem. A transformer has reactive drop of 6% and the resistance drop of 2.5%. Determine the lagging power factor at which the voltage regulation is maximum and the value of regulation. So the resistance drop and reactant drop is given. The power factor, we need to find the power factor, lagging power factor, and the condition given is voltage regulation is maximum. And also we need to find the value of the regulation, right? So the two data given in this problem is resistance drop and reactance drop. Resistance drop VR is taken as VR, that is nothing but I2 R02 divided by no load secondary voltage, that is equal to 2.5%. Similarly the reactance drop Vx equal to I2 X02 divided by no load secondary voltage, that is given as 6%, that is 6. So we have two data VR and Vx. Now we will see what is the condition for maximum efficiency. Maximum regulation, not efficiency, maximum regulation is tan pi equal to X02 divided by R02. So the regulation will be maximum at this condition, tan pi equal to X02 divided by R02. So first we will find the X02 and R02. So VR is given I2 R2 divided by no load secondary voltage, that is 2.5. So from that R02 multiply this secondary voltage here and bring these two terms in the denominator. So that R02 equal to 2.5 into no load secondary voltage divided by I2. Right. So this equation is rearranged in so that we can find the R02 value. Similarly Vx is given as I2 X02 divided by no load secondary voltage, that is 6. Now multiply, bring this V02 in the numerator, bring the I2 in the denominator. So that X02 equal to 6 into no load secondary voltage divided by I2. So from the resistive drop and reactance drop, we frame the equation for R02 and X02, right, in terms of no load secondary voltage. Now we can substitute these two values for a maximum regulation. So the condition for maximum regulation is tan pi equal to X02 divided by R02. So the X02 is nothing but 6 into no load secondary voltage divided by I2. Then R02 is nothing but 2.5 into no load secondary voltage divided by I2. So this I2 got cancelled, no load secondary voltage also got cancelled. So what we have 6 divided by 2.5, right? So tan pi equal to 6 divided by 2.5. So 6 divided by 2.5 is 4. So that tan pi equal to 4. From that pi equal to tan inverse 4, that is equal to 67.38. So the pi value is 67.38. From that we can calculate the power factor. From that we can calculate power factor value. So pi value is 67.38. So that cos pi equal to cos into 67.38, that is nothing but 0.385 lagging, right. So the first question we need to find the power factor for lagging, that is nothing but 0.385. Next we need to find the maximum regulation. So this is the condition for maximum regulation. At this condition we got the power factor as 0.385. Next we need to find the maximum regulation also. In that we need a sin pi value. So that sin pi equal to sin 67.38, this value. So that is nothing but 0.923 lagging. So this is the cos pi value, this is sin pi value. So by using these two we can able to find the maximum regulation. So the maximum regulation equal to VR cos pi plus Vx sin pi. So VR is already given, it is 2.5. Cos pi value is 0.385, that we calculated, and Vx is 6%, 6. Then sin pi is 0.923. So all values are substituted. So by simplifying this we got 6.5%. So the regulation for a maximum regulation is 6.5%. For that, under that maximum regulation, the power factor is 0.385 lagging. The corresponding value of sin pi is 0.923 lagging. So in this problem, we calculated the power factor for maximum regulation as well as the value of maximum regulation for that given condition. The data given is voltage drop and reactant drop, resistance drop and reactant drops are given. So we discussed two problems based on the regulation. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the losses and efficiency of the transformer part 1. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we'll go to the problem. The OC and SC test, that is open circuit and short circuit test on 10 kVA 125 bar 250 voltage 50 Hz single phase transformer gave the following test result. For OC test, open circuit test, 125 voltage is 125, the current 0.6 ampere, the power is 50 watts, that is performed on the low voltage side. Short circuit test, AC test, 15 voltage 30 ampere 100 watts, power is 100 watts, that is on the high voltage side. Now we need to calculate the copper loss at full load. Full load efficiency at 0.8 power factor leading. Half load efficiency at 0.8 power factor leading. Regulation at full load 0.9 power factor leading. So we need to find the four different values. Copper load at full load, copper loss at full load efficiency at 0.8 power factor leading, half load efficiency at 0.8 power factor leading, voltage regulation at full load 0.9 power factor leading. First we will see the copper loss on the full load. So copper loss on the full load is I2 square R02 or I1 square R01. So copper loss is nothing but I square R. So either here we can refer either the primary side or secondary side. I2 or I2 square R02 or we can take it as I1 square R01. So the data available is the short circuit voltage is 15 voltage, short circuit current 30 ampere, the power during the short circuit test is 100 watts. Then V1 is 125 voltage, V2 is 250 voltage, the frequency is 50 Hz, the rating of the power transformer is 100 kVA. So this data for short circuit test. Similarly, the open circuit test data is also available. From that we can find the Z02, the impedance in the secondary side, equal to Vs by Isc. Finally, what we need is X02, so that we are finding Z02. Vsc divided by Isc, that is 15 divided by 30, 0.5 ohm. Similarly, Isc square R into R02 equal to Wsc. The power short circuit power is nothing but power reading from the short circuit test is Isc square into R02 because it is short circuited. From that R02 equal to Wsc divided by Isc square. So 100 divided by 30 square, it is 0.1111 ohm. Now we calculated the Z02 and Isc and R02. By using Z02 and R02 we can find the impedance X02. So these data are needed for finding the copper loss. So X02 equal to square root of Z02 minus R02 square. So that is square root of 0.5 square minus 0.111 square. So the value is 0.4875 ohm. Now in order to find the copper loss we need the full load current I2 equal to kVA divided by V2. The power rating of the transformer divided by V2 will give the current value. So it is given as 10 kVA. So 10 into 10 to the power 3 divided by V2 is 250. So by simplifying that we got 40 ampere. The full load current is 40 ampere. Right. So now we can able to calculate the first question, full load copper loss. I2 square into R02. I2 is calculated here, R02 is also available. So by using these two values, we can able to find the full load copper loss. I2 square into R02, that is 40 square into 0.111, that is nothing but 177.78 watts. So the full load copper loss is 177.78 watts. Now we'll go to the second question. Efficiency at 0.8 power factor leading. The second question is efficiency at 0.8 power factor leading. So the efficiency at the full load is output divided by input, right? So that can be, the input can be written as output plus losses. Output divided by output plus losses. The input is not given, output rating is given, so that we can convert this input is nothing but input is converted into output plus losses. So the output is nothing but V2 I2 cos phi 2 divided by output V2 I2 cos phi 2. The losses is nothing but iron loss and copper loss. So this question we are discussing for full load, the W, the iron loss plus copper loss. So all these values are available. So V2 is 250, I2 just now we calculated 40 into power factor is given as 0.8 in the question itself given. So 250 into 40 into 0.8, this is 50. This is nothing but iron loss. So the no load power is nothing but a iron loss. During no load, the current variation is very less. The loss happen is only due to the iron loss. We are assuming that there is no variation in the current during iron loss during the open circuit test. This copper loss just now we calculated 177.78 for a full load. Copper loss will vary with the current. When the current increases, copper loss also increases. But this iron loss will be constant for all the loads. The iron loss will not vary with the current, so that we can take as it is. So by simplifying this, what we got, 97.23%. So the efficiency at full load 0.8 power factor is 97.23%. Now we'll go to the half load. Efficiency at half of the full load. So when the load is half of the load, the current, we need to find the current of half full load. When the load decreases, the secondary current also decreases. That is nothing but 1/2 into 40, half of the current rating. So this 40 is the full load current. For half load, automatically 40 divided by 2, it is 20 ampere. So with this current value, we can find the efficiency. So this is nothing but output divided by output plus iron loss and copper loss. This HL refers the half load, the current at the half load, copper loss at the half load. We need to find the half load, because full load means 40 ampere, automatically half load the current become 20 ampere. Similarly, we need to find the copper loss also. So the copper loss at full load is I2 square R02. We know that it is. For a half load, it is automatically I2 divided by 2 the whole square into R02. Right? At the full load, the current is I2, means half load automatically it is I2 divided by 2. So 40 divided by 2 the whole square into 0.1111, that is nothing but 44.44 watts. So this is nothing but the copper loss at the half of the load. This iron loss is always constant. It is irrespective of the load. It will not change, it's constant. So that we can take it as it is, 50 watts as a copper loss. It will not vary with the current, but this copper loss will vary with the current. So that is calculated as 44.44 watts. Now we'll calculate the efficiency. So efficiency equal to V2 I2 at the half load into cos phi 2 divided by V2 I2 at the half load into cos phi 2 plus iron loss Wi plus copper loss at the half load, that also we calculated. So 250 into 20. The full load current is 40, the half load current is 20. 40 divided by 2, 20 into 0.8. The power factor is given as 0.8 divided by 250 into 20 into 0.8 plus this iron loss. Iron loss will not vary with the current, so that is take as it is, plus half load copper loss. Thus now we calculated 44.44. So by simplifying this, we got 97.69%. So the efficiency at the half of the load at a power factor of 0.8 leading is 97.69%. Now we'll go to the fourth question. regulation at full load 0.9 power factor leading. We need to find the regulation at full load of 0.9 power factor leading, right. So cos pi equal to 0.9. So automatically pi equal to cos inverse 0.9 means 25.84. The angle pi is 25.84. So the regulation formula is percentage of regulation equal to I2 R02 into cos pi minus I2 X02 sin pi divided by no load voltage into 100. So all these values are available. I2 is the no load current, no load secondary current 40 into R02 already calculated 0.111. Then cos pi is given as 0.9 minus 40 into X02 is 0.4875 into sin pi. Pi value is 25.84. So sin 25.84 into 100 divided by no load. The no load secondary voltage is 250. So by simplifying this, what we got, regulation equal to minus 1.8013 percentage, right. So we got the regulation in the negative. So in this problem, in this question, we calculated the regulation and the efficiency at full load, efficiency at the half load, and copper loss at the full load. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the losses and efficiency of the transformer part 2. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we'll go to the problem. Find the all day efficiency of 1500 kVA transformer whose copper losses and iron losses at full load are 4.5 kilowatt and 3.2 kilowatt respectively. During the day of 24 hours, it is loaded as follows. So this number of hours is given, load in kilowatt and power factor. For number of hours 6 means the load in kilowatt is 1200, the power factor is 0.8. The number of hours 10, the kilowatt is 900 and the power factor is 0.75. And the number of hours 4, the load is 300 and power factor is 0.8. For another 4 hours, there is no load and no power factor. So this is the data given for entire 24 hours. By adding this, we can get 24 hours. So we need to find the all day efficiency. I will see the given data. So the 1500 kVA is given. The rating of the transformer is 1000 kVA. At full load, the copper loss and iron loss is given. Copper loss is 4.5 kilowatt. Iron loss is 3.2 kilowatt. So the full load output is 1500 kVA. Full load copper loss is 4.5 kVA. Full load iron loss. Iron loss is irrespective of the load. So the iron loss equal to 2.2 kilowatt. This is 3.2 kilowatt, not a 2.2 kilowatt. It is 3.2 kilowatt. So the all day output, we need to find the efficiency. For finding the efficiency, we need output and input power. So first we will find the all day output in kilowatt. So from the tabular column, for first 6 hours, the output is 1200. For next 10 hours, the output is 900. For next 4 hours, the output is 300. For another 4 hours, the output is 0. Right. So these data are multiplied. Finally, we got 17,400 kilowatt for a 24 hours. 17,400 kilowatt. So we calculated the output. Now we need to calculate the input. Right. So the iron loss for 24 hours equal to 2.2 into 24 means 76.8 kilowatt hour. Iron loss in 24 hours is 3.2 into 24, that is 76.8 kilowatt. So now we calculated the output and iron loss for 24 hours. When the copper loss, when full load copper loss is given, then the copper loss at particular load we need to find, because it is given for the hours, 10 hours, 6 hours are given. So the full load copper loss is already given, but we need to find the copper loss at a particular load. So how will you find? Full load copper loss multiplied by load kVA divided by actual kVA square. So by finding this, we can find the copper loss for a particular period, because in tabular column is given, right. So the load kVA and actual kVA. How will you find the kVA? kVA equal to kilowatt divided by cos pi, that is power factor, kilowatt divided by power factor. So the load kVA and actual kVA we can use by this formula, kV divided by power factor, so that we can find the copper loss for a particular load. So copper loss for 24 hours is 6 into 4.5. So this is the 6 hours. This 4.8 is the copper loss for a kVA. This is the kVA is 1200 divided by 0.8. So this is the loaded kVA divided by actual kVA is 1500, right. So this is the number of hour. This is copper loss, full load copper loss. This is the kVA rating given. This is kVA for this 6 hours divided by power factor, so that it is divided by power factor is square, so that we will get the copper loss for this 6 hour. Similarly, for the next 10 hours, the copper loss, that is 4.5, it is 900. For the next 10 hours, the kVA rating is given 900 and power factor given 0.75 divided by 1500 square. Similarly, for the next 4 hours, the rating is given 300, power factor is 0.8 divided by the actual power, actual kVA is 1500. The square is there, right. So this is the copper loss calculated for 24 hours, 6 hours, then next 4 hours, next 10 hour and next 4 hour. Remaining 4 hour the power is 0, right. So this first term refer the number of hour, second term refer the copper loss, full load copper loss. This one is nothing but kVA rating. This is the kVA for the particular 6 hours divided by power factor for the particular 6 hours. So all the data are multiplied. After simplification we got 56.925 kilowatt. So this is the copper loss for a full load for a 24 hours. This 4.5 is the copper loss for a full load copper loss. This is for a particular load for a given time period. It is multiplied and we calculated the copper loss for entire 24 hours. Now we got the output power as well as losses. From that we can able to find the efficiency. All day efficiency is nothing but output in kilowatt hour divided by input in kilowatt hour. Output in kilowatt hour, this input is written as output in kilowatt hour plus iron loss and copper loss, because output is available, kVA rating is given, input is not available, so that input is converted into output plus losses, right. So the output is 17,400 that we already calculated, divided by 17,400 plus 76.8. This is nothing but a iron loss for a 24 hours plus 56.925. This is nothing but copper loss for 24 hours. So output divided by output plus iron loss plus copper loss is nothing but a efficiency. So after simplification we got 99.24%. So the efficiency, all day efficiency is 99.24%. So in this problem we calculated the all day efficiency for a given particular tabular column is given, for the load condition is given, based on that we calculated. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is available in the description box. Thank you for listening.